Hello everyone. Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from the Electrical Engineering Department at IIT Hyderabad. And today we will begin with a completely new module which is related to NAND flash, which happens to occupy the most of main storage in modern day computing systems. So this lecture or this module presents a very interesting transition because we are transitioning away from memory devices. Remember, we studied about SRAM memory, which formed the L1, L2, and L3 cache. Next, we went to study the device and the system architecture of DRAM, which constituted the main memory. So today, we will begin our study of studying about from memory to storage. We will transition from memory to storage. Just a very quick reminder. Remember that memory devices were primarily for the objective of fulfilling the immediate computational needs of the CPU subsystem. And therefore, they were very tightly integrated with the CPU subsystem. And therefore, all the focus was on performance. That is trying to reduce latency. And we saw that DRAM and SRAM subsystems did a great job at that. Now the context is going to shift a little bit. There is going to be a shift in context because in storage, the primary motivation is not really performance, but it is the ability to hold on to data for long periods of time. So the first thing that we will try to focus on when we try to understand NAND flash devices or especially flash memory is that it is a form of non-volatile storage. By non-volatile storage, I mean that once you switch off the power supply, the data which is stored in the NAND flash should not be lost. The other very important aspect is that of very high bit density, or you can also say of very low cost per bit. That is the other very keen focus when we move from memory devices to storage devices. And all of this, as you know, happens at the compromise of cost. And this is what our pyramidal hierarchy also indicates. Near the logic subsystem, you have 60 SRAM cell, 1T or 1C DRAM cell. So they occupy significant amount of space. Now we will begin our study of non-volatile storage element known as the flash cell. And then we will go to NAND flash, where the focus is on high bit density while compromising on the speed. Okay, so where does it sit in our memory hierarchy? If we flatten it out, it sits just after our main memory. And it is the job of the main memory subsystem to retrieve information from the primary and secondary storage elements, right? It is very important to recognize in context of what we just discussed, that now we will focus more on bit density and not so much on latency. Just like there was a memory wall between the CPU subsystem and the DRAM subsystem. Why did this memory wall exist? Because the throughput of DRAM subsystem was much slower compared to what the data requirements are from the CPU subsystem. So there was a mismatch in bandwidth. Similar mismatches are going to become very apparent when we look at the interface between the main DRAM memory and the secondary or primary storage elements, right? Why is this the case? Because DRAM subsystems work in the order of tens or few hundreds of nanoseconds. But we will see that there will be a big change, a big gap in the access times or the read-write times of flash devices, which will be in the order of hundreds of microseconds or even 1 millisecond. And as you know that we had discussed, the new kind of storage elements called storage class memories, which are two terminal elements, are trying to fill in the gap. But those are a little futuristic things which we will study a little later from now. Now we will study what is the staple mainstay of storage systems, which is the NAND flash. A very important thing to notice is this mismatch in latency causes big problems in bandwidth mismatch also. And this bottleneck is often known as the IO bottleneck. And this IO bottleneck becomes a very serious concern, especially for data-driven computing like AI/ML computing. And this is how this NAND flash technology that we will discuss. So we have to look at NAND flash technology in this particular context. What the NAND flash technology has done is it has kept these considerations in mind, and it has tried to make up the problems in latency, the slow latency or large latency, slow read and write speeds. It has tried to make up somehow by dealing with large chunks of data at one given point of time. And this is what you need to remember when we go ahead and study NAND flash. It will be slow, but you will see at one point of time, you will be able to access large chunks of data from this storage subsystem. So just a very quick word about where this terminology NAND flash comes from. You might be wondering about it. So the flash is a rather historical term, and we will see that in flash, original flash cells, this word flash, which means quick, fast, it means it was more like a marketing term historically to indicate that large chunks of data primarily are being erased at the block level. So in a flash, you are able to write data, read data. Here, the flash is not really with the speed, but the large chunk of data that you are getting access to. Okay. Currently, the term flash has slightly changed meaning and context. The current use of flash is generally to indicate that the subsystem has non-volatile storage, or the cell has non-volatile storage. Now coming to the first term, which is NAND. What is this term NAND? NAND is a very important term here because it relates to the array organization. We have been seeing throughout in our study, especially in DRAM, that just designing a memory cell or a storage cell is not enough. There has to be a lot of effort and intelligence put into design of the array subsystem and also the peripheral architecture. Then only you will be able to fulfill the requirements that is needed from that particular memory or storage element. And this is exactly what the term NAND here indicates. It's a way to organize these flash cells in ways which allows the program and erase of large chunks of data. Okay. So with this introduction, let us start looking at a very brief historical perspective in the development of flash cells. Okay. So just to make you understand, maybe the newer generation may not be familiar with it. Actually, solid state drives or NAND flash was not the staple when computing systems started to evolve. As you may know, the main computing for computing systems, the main storage element which is still used in some servers and some little low generation computers and even laptops is something called magnetic disks. So the magnetic disk is a very simple device. By switching the magnetic polarization from a read-write head, which is a mechanical read-write head, you are able to write bits into this magnetic disk. The principle is same to the old gramophones that we might have seen in the movies. Now, this had limitations. It had very high bit densities, but it had limitations in read-write speeds and also in scalability. So people started looking at other ways, and optical disks, you might have seen CD drives, compact disk drives, were an alternative which was also being used a few generations, even 10 years earlier. However, all of that has been now replaced by solid state drives. And it was very important to note what is that specific distinct advantage that solid state drives give, which enable this transition from magnetic and optical disks to purely solid state devices. And the key advantage is that of reliability and scalability. What do I mean by reliability and scalability? So why are solid state drives very scalable? This is simply because they do not have any mechanical moving parts. As you can see, both the magnetic disc and the optical disc had moving parts. So the magnetic disc had a rotating chuck, and you had a mechanically moving read write head. This is the mechanically moving read write head, which I have just indicated. Whereas the optical disc also had a rotating part. However, your solid state discs are entirely based on the manipulation of electronic fields or electrical fields, and therefore they do not require any moving parts. This makes them very reliable because there are no mechanical moving parts, and very scalable. Of course, the scalability has also come with real advances in nanofabrication technology, as we have been seeing for other solid state memory devices like SRAM and DRAM. So the history of solid state drives is rich, but we will focus mostly on flash memories. But just for your information, the actual beginning of solid state drives began from the 1950s, where Wen-Sing Chow discovered the programmable read-only memory. So this is the programmable read-only memory discovered in 1956. So the programmable read-only memory is a rather simplistic device. It contains arrays of electronic fuses. Just like in your home, you have an electrical fuse box. You have an element, a kind of metal element, and if there is a surge of current, this fuse simply breaks. So from low resistance state, where the fuse is intact, when the fuse melts and breaks, it becomes a high resistance state, and it cuts off electricity to the rest of the home, therefore protecting against any surges. Similar is the concept of a programmable read-only memory. In a programmable read-only memory, you have the small electronic fuses. These could be metal insulator, metal junctions also. In these cases, what happens is, at the beginning, all the array elements are pre-coded to 1 because everything is working. Then what you do is, only onto certain bits, you pass a large current and you make the fuse to blow up. Therefore, the 1 becomes a 0. This can only be done once, and therefore it was called a programmable read-only memory. Once you burn the fuse, the data is permanent. And it will be interesting to note, programmable read-only memories are still being used for many security applications where the information needs to be hard-coded and needs to be protected against manipulation. This change happened when people realized that just having read-only memory, which is changed just once or blown just once, has very limited use. So people started exploring electronically erasable or electrically erasable programmable read-only memories. This was discovered in late 1970s, and this was the first flash cell. So this also had a floating gate transistor, but it looked very different from the flash cell that we will discuss. The idea was very simple. This was electrically erasable. So you could do a little bit more cycles of read and write, but of only write, but it was always read only. Cut to 1984, where the hero of our story, which is the flash cell, was finally manufactured by Toshiba. And that is what we will see in the next slide. In 1987 was very momentous in the sense that the individual flash cell was for the first time commercialized and integrated into the NAND flash array, which gives you these large bit densities. And of course, we should mention that in 2009, for the first time, we were able to have a handheld device, which was a USB driven device. You can just connect it to a USB port to your computer, which had more than 1 TB of data storage. So 2009 was very momentous, and that is when I would say that solid state drives, the promise of solid state drives, which were initially much more expensive compared to magnetic and optical discs, really took off. Okay, so as we know, the way to drive down cost is to improve the bit density, and that is the entire story of NAND flash. Okay, so again, going back to a very brief history of the flash cell. Very interestingly, the flash cell was invented in the same place where the transistor was also invented. And incidentally, it was invented by one of the same persons. If you know a little bit of history of the transistor, the first patent or first demonstrations of transistors came from Kang and Attila in Bell Labs. In this time, the flash cell, which was nothing but a floating gate cell, we will study what a floating gate cell is. A floating gate transistor is nothing but a modified version of the normal transistor, was first invented via a patent in 1967 in Bell Labs by Kang and Z. Few of you might know Simon Z. He was a great electrical engineer who has written the Bible for semiconductor devices, which a lot of us do follow. Okay, so but it is important to mention that in the history of NAND flash, although this was just an idea which came from Bell Labs, the manufacturing and commercialization was done by Fujio Masuka in Toshiba. In 1984, for the first time, they were able to make a fabrication of the NAND flash cell. And by 1989, they were able to have these small pen drives which came out into the market. So this is something that a slightly older generation will remember is a pen drive. A pen drive had just like a pen kind of a structure. One end had a USB kind of thing jutting out of it. And inside, if you open the metal casing, you would see that there is a NAND flash cell and there is another driver circuitry all integrated in a printed circuit board. Okay, so with this very brief history of flash cell, let us now transition to understanding things a little bit more technically. So next section, we will try to understand what is the flash cell and how does it work. So as I just mentioned, the flash cell is nothing but a slightly modified version of your MOSFET. So therefore, to understand the flash cell, it will be important to have a very quick recap of the MOSFET. Now, MOSFET is a rather complicated device to cover in few slides, but I will try to pick up the elements which are absolutely essential to understand the behavior of a flash cell. So most of you might be familiar with this structure of a transistor. In front of you, I have presented a NMOS device or a NMOSFET. An NMOSFET constitutes of a P-type substrate, which is marked here in blue, and heavily doped N+ regions which behave like the source and drain of the transistor. So generally, the source end of the transistor is grounded. The substrate also we can consider to be grounded for all practical purposes. And you apply a drain bias at the drain terminal. And the expectation is that the gate terminal, which consists of a heterostructure of oxide and metal. So the gate oxide, a very thin gate oxide that I have indicated here in very light blue color, and the metal is what is responsible for turning the transistor on and off. Let's see how. So what essentially happens is, this is something called the transfer characteristics of a transistor. What is transfer characteristics of a transistor? The transfer characteristics of the transistor indicates what happens when I keep the drain bias constant. So I have fixed a small drain bias. Remember, source is grounded, and this MOSFET, I'm sweeping the gate voltage. When I change the gate voltage, see, the x-axis or the independent axis is the gate voltage. I try to see what is happening to the drain of the drain current of the transistor. And as we see earlier, so let us focus only on the linear regime first. The earlier we see that very slow, less amount of current, negligible amount of current is flowing through the transistor. But as I increase the gate bias further, there is a sharp increase in the drain current. And this transition from having almost no current to significant amount of current in the order of milliamperes is called the onset of the on condition. Okay, so very briefly, the transistor based on this on condition can be classified into two regimes. One is your above threshold region, or which is also colloquially called the on state of the transistor. On state because the transistor has now turned on. And the other is your sub-threshold region where the transistor is off, okay, because it is showing very low current. The transition voltage in the gate axis or the gate bias, which is where the transition happens from the off state to on state, is something called the threshold voltage of the transistor. Threshold voltage of the transistor is something that we will focus on throughout the study of flash cell. So I hope to repeat it once again for you. The transistor can be switched on, in this case this NMOS, when you increase the gate bias from let's say 0 volts at around roughly 1.5 volts, we see that there is a sudden shoot up of the current, and this transition is known as the threshold voltage of the transistor, or the gate voltage where this transition occurs from off state to on state is known as the threshold voltage of the transistor. Some of the people who are more interested in device physics might have already studied during the threshold voltage of the transistor something called the inversion charge. Let me point out where this inversion charge happens. Something called the inversion charge appears at the interface of the oxide and semiconductor. So at the oxide semiconductor interface, there is an inversion charge. Why is it called an inversion charge? Because this inversion charge is consisting of electrons which join these heavily doped N plus regions. So it is called inversion charge because the original substrate is p-type. So only at the interface, at the surface, an inversion of charge is happening. Okay, with this understanding, let's move forward and ask a very important question. Good, we know how the transistor works. But remember, a transistor is essentially a switching device or a logic device. Why is it a logic device or a switching device? Because by controlling the gate bias, you can turn the transistor from on state to off state and vice versa. The question we are trying to ask, however, is how can this logic device or a switching device be transformed into a memory device? And the answer lies in, again, focusing on the threshold voltage of the transistor. Remember, the threshold voltage of the transistor is that which indicates how much is the gate bias which is required to make the transistor to go from off state to on state. So let us consider this particular example where you have a transistor called transistor 1, which I have indicated. So what is the x-axis? The x-axis is the gate bias, and the y-axis, just like in our previous graph, is the drain source current. So in this transfer characteristics, we see that transistor has some threshold voltage, and this threshold voltage happens to be less than some arbitrary reference voltage which we have selected. So we can say that at the reference voltage VG ref, this particular transistor is off simply because the reference voltage of the transistor is small, or rather the threshold voltage of this transistor is greater than the reference voltage. Similarly, we can define another transistor where the reference voltage is greater, or the threshold voltage of the transistor is greater than the reference voltage. And therefore, while transistor 1 was off by the virtue that VT1 is greater than VG ref, in the case of transistor 2, for the same reference voltage, as you can see, there is a finite current that is passing through the transistor. Okay, so this is a very important thing to understand, that for the same gate reference, transistor 1 is off and transistor 2 is on. So a natural question that comes to mind is, can we design a structure such that the threshold voltage of the transistor can be dynamically tuned from VT2 to VT1 and vice versa? So you have to dynamically tune the threshold voltage of the transistor. And if you can somehow do some modifications to the transistor such that the threshold voltage of the transistor can be dynamically tuned, you will come up with a memory device. Why will this be a memory device? Because when VT2 is less than VG ref, it will behave like in a low resistance state because current is flowing through it. However, when VT1 is less than VGREF, VT1 is greater than VGREF, it will behave like the red curve and it will be in the off state. So let us try to understand how can we design a device which can have tunability of threshold voltage of transistor. So to do that, what we need to do is have a little bit of more thorough understanding of what it means, a little bit inner mechanisms regarding the threshold voltage of the transistor. So the threshold voltage of the transistor, more basically, I'm trying to simplify things as much as possible, can be divided into two parts. One is the ideal component of threshold voltage of transistor. What do I mean by ideal component? That it is a perfect transistor. There are no defects in the transistor. There are no non-idealities in the transistor. Just by the virtue that you have some geometrical parameters like Cox and you have doping constants, it will have some finite threshold voltage. The other component, which is the component of our interest, is the flat band voltage of the transistor. This flat band voltage can tune the threshold voltage of the transistor dynamically because that depends on some non-ideal factors like fixed charges and traps or trapped charges inside the oxide layer of the transistor. Let us discuss how that happens. So first, let's discuss about the ideal case. Let's look at what the ideal case will look like, where the trapped charges inside this oxide is absolutely zero. So I have reproduced the schematic of the transistor, and below is something called the band diagrams. So what is band diagrams? Band diagrams are what happens to the conduction and valence band within the semiconductor when you start applying a gate bias. And how we are checking the band diagram? It is a cross-sectional diagram. What is cross-sectional diagram? It means that you are taking a cross-section from the metal to the oxide to the semiconductor. So here, this is the metal, this is the oxide, and this is the semiconductor. So with this information, let's see what the band diagram looks like when there is zero gate bias. So when there is zero gate bias, for an ideal case, the bands look absolutely flat. What do you mean by flat? That there is no curvature of the bands in the conduction band or even in the valence band. So now what are we trying to do? We will slowly crank up the gate bias such that the transistor turns on. Remember, what is the condition of turn on of the transistor? There should be an inversion layer which forms at the interface of the oxide and the semiconductor. Currently, in the flat band condition, the number of electrons which is there at the interface of the oxide and semiconductor is very little. Why? Because the Fermi level is closer to the valence band. This simply means that the entire region is p-type. Now what we do is we apply sufficient gate bias such that the number of electrons at the interface, by the virtue that the bands have now bent because of the application of this gate bias, are such that this Ns, or the number of electrons at the surface, are equal to the number of holes in the bulk substrate. In this condition, you have said to be reached the threshold voltage of the transistor. So in other words, the threshold voltage of a transistor is reached when the number of surface electrons is equal to the number of holes in the bulk. So we see that there is a finite threshold voltage to be reached even for an ideal case. Now let's look at the non-ideal case. In this non-ideal case, what we have considered is, as I have indicated with red dots, there are some negatively charged traps which are embedded permanently inside the oxide interface, inside the oxide. So what will happen to the equilibrium bands? By equilibrium bands, I mean what will happen when the gate bias is zero. As you can see, there is a significant change in the so-called band structure or band diagram when there is negative charges. Why? When there are negative charges embedded inside the oxide, it will cause a induction of positive charges near the surface. So earlier, as you see, number of electrons were low, but near the surface were low. Now they are even lesser. Why? Because the bands have moved up and there is an accumulation of holes near the surface. In this kind of a scenario, as you can understand, it will be even more difficult to reach the threshold condition. Why is that the case? Because first, the gate potential has to make sure that the bands which were tilted upwards first need to reach flat band condition, and then furthermore they need to go down. Okay, so it is very clear that in the case where there are negative trap charges at the oxide, the gate voltage has to work much harder. Therefore, the gate voltage has to be much more compared to the ideal case to reach the same condition as NS equal to P0. And that is exactly what we will notice when we look at the transfer characteristics of the transistor. When we look at the transfer characteristics of the transistor, we will see that when Q trap was 0 or ideal, the threshold voltage of the transistor was relatively much lower compared to the threshold voltage of the transistor when Q trap where there were negative trap charges. And if we have these ideal Q trap equal to 0 and Q trap less than 0, to have significant differences in threshold voltage, we can choose a reference voltage in the gate or gate reference voltage, where in one case the transistor will be on, which is the Q trap equal to 0 case, and in another case Q trap less than 0 case or negative Q trap, the channel will be off. So in one case it will be on, the other case will be off. So now we have understood in this particular slide that by the most practical way of tuning the threshold voltage of the transistor to transform a MOSFET device into a memory device is to play with the trap charges. So the next question will be, of course, how can we reliably introduce and remove the trap charges into the oxide layer of the transistor? And this is where the modification part of the transistor will come. As you can understand, all the action of Q trap is happening only at the oxide and semiconductor or oxide and metal part. So it makes sense that this can be facilitated by making design changes to the gate stack of the transistor. And as we will see in the next class, that happens through the addition of an charge storage layer. So a charge storage layer will contain these charges, will hold on to these charges permanently till you remove them, and they will and you will be very easily be able to store and remove charges from the charge storage layer, which will tune the threshold voltage of your modified transistor, which is nothing but a flash cell. Okay, with this, let's stop in this lecture, and in the next lecture, we will look at the structure of a flash cell. Thank you very much.